In the last lecture, we have at the end come to Fourier's equation, which we wrote in the following way: the heat flux per unit time and per unit area by conduction in some medium can be expressed in the following form: is minus K, the thermal conductivity, times the temperature variation per unit length along a normal, or let's say along a heat flow line. Just to repeat what this equation really means is the following: that if we have a medium in which we have a temperature field, and if the temperature field is unsteady, this means it changes somehow in time, then there will be surfaces of constant temperature. Now these surfaces, if the situation is unsteady, will move through the solid material in order to calculate at a certain instance and at a arbitrary location in the solid body the heat flux per unit time and per unit area. We think of the temperature field frozen at this moment, so that we have then some, if it would be a two-dimensional situation, some surfaces which are isothermal surfaces, which in a two-dimensional case would be just the same at any cross sections here parallel to the blackboard. We would have, we could select now a point, and we want to calculate with this equation the heat flux at this time where this picture represents our isotherms. Then we find a heat flow line which is normal to the isothermal surfaces. We pick up a infinitely small or very small surface area within this isothermal surface, and as we have done before, in order to indicate that it is a very small area, we would call this area dA. A is symbol for the area, and D as a so-called operator, really just indicating, reminding us that we are dealing with a very small surface area. We have to take a small area because in general the heat flow per unit area will change along the surface, and therefore if we want to have a local condition we have to refer it to a very small area. Then the heat flux would be Q equal the amount of heat which per unit flows through this surface area, which will be again a very small quantity, dQ, divided by dA, so that we get the heat flux per unit area. Then along this normal we would measure the temperature variation. We find out what in this direction is the temperature variation per unit length, and that is just this quantity. If we measure the length along which we measure in order to get this ratio, the temperature difference, if we make this quantity again very small, so that we get again the local condition there. Now, these are partial differential signs. This means they indicate to us the procedure which we have made. We consider the situation at a certain moment, so we keep the time fixed, but we change we find the temperature variation along the normal n. Okay, so if we would know the temperature field, then we could calculate the heat flux with this equation at any location. In general, we don't, and actually one purpose of the analysis is to calculate now, to determine, and in certain examples, the temperature field in various bodies. For this purpose then, since we have really in our equation two unknowns, we don't know the temperature, we don't know the heat flux, we have to get some other considerations. We assume that the conductivity, which is a property of the material, is known. So Q and T are here the dependent unknowns. So we have to make some other consideration, And we get this, as I mentioned the last time, from a heat balance. Now, we will at the moment make the heat balance on a stream tube. We know that such a stream tube we could, for instance, construct by considering all the heat flow lines around the periphery of our area element dA. In this way we have a stream tube, and again, in order to get a local consideration, we make the width of our stream tube very small, so we use an area element to construct our stream tube. And now I will draw this stream tube once more. Maybe I draw the area element dA now in perspective, so that it is clearer. Then this would be two of the many heat flow lines. This is in the area element dA. This would be, we can pick out one heat flow line, which is the axis of our stream tube. And we want to make a heat balance on a small element of this stream tube with a length, let's say dn, very small length dn. So that we would have another cross-sectional area here. Now we ask what kind of heat flux or heat contributions to the material in this element of the stream tubes occur. We know that, as we have discussed before, that heat flows only within a heat tube. It cannot cross the walls of a heat tube, so that we will have a heat flux entering through this cross-section dA, which I will call dQ. We will have a heat flux leaving on the other side, which in general will be different from this one here, so I call it dQ dash. We will have no heat flux crossing through the periphery of our stream tube. Now, in general, we may have a heat generation in our interior. For instance, if some chemical process occurs. Could be exothermic, so that by some chemical process heat is developed in the interior. It could be an endothermic chemical process, so heat is absorbed in the interior, is used up in the chemical process. Now, in a general way, then we can express this in the way that we have heat sources or heat sinks, which either generate or absorb heat. And we will call, and we have to introduce something to express the strength of these heat sources. We will call the heat which is developed by some heat source, capital phi, as, which is developed per unit volume. And if the phi would be negative, then it expresses a heat sink. If it's positive, it expresses a heat source. Then the heat which is generated within our volume element is equal to phi times the size of our volume element. The size of our volume element is, since it is a cylindrical shape, cross-sectional area times height of the cylinder. There is dA times dN. And this would be, if this is the heat source, the heat generated per unit time, then this gives us the heat which is generated in our volume element per unit time. Let's call this Q, and it will be an infinitely small quantity, surely, because the volume element is infinitely small, dQ source. Then we have the heat flux entering, we have the heat flux leaving. The difference, for instance, between dq minus dq dash would be the surplus of heat which enters the volume element over that which leaves the volume element. So this would be a continuous heat which accumulates in the interior, and also the heat which is generated internally will have to be stored in the interior of our volume element. We know that a material can store heat if the temperature increases, and the parameter which we use, the property to indicate the storage capacity, is the specific heat of the material, which gives then the heat which can be stored per unit mass. We will refer it to a unit mass, and per unit temperature increase. So in this way then we want to write down an equation for the amount of heat which is stored per unit time in our volume element. First we have to, since the specific heat refers to a unit mass, we have to find the mass of the material in the volume element, and we find the mass by multiplying the volume with the density. The volume we have here already. So we write dA times dN, which would be the volume, times the density rho. Then, if we multiply this with a specific heat, the symbol for this is generally lowercase t, then this gives us the heat which is stored if the temperature decreases by 1 degree, by unity. Now, in reality, the temperature will rise by some amount which we do not know, which by some amount dt. And we want to have the heat which is stored per unit time. So we want to have the temperature rise per unit time. So we have to write this dt, and I'll explain immediately why I use again this partial differential sign, divided by the time during which we have this temperature rise dt, which is a differential. And now a symbol for the time, I will use the Greek letter tau, because we have used the t already for temperature. So tau is our symbol for time. And we want to know how the temperature changes per unit time in this fixed element. So therefore we say here we want to have the temperature change with time, but at a fixed location. And this is the fact which is indicated again by the partial differential sign. This means we are only interested in the change of the temperature with time, not in the change with location. Okay. And then now we can write our heat balance. Obviously, all of the net heat which goes in and which has to be stored in the interior of our volume element will be the following. By heat conduction, we get into our volume element dq minus dq dash. No, everything is per unit time. Okay. Well, it would still be, because the volume element is infinitely small, it would still be an infinitely small quantity. Okay, so this is the heat entering the volume element by conduction, again, per unit time. We consider all of our quantities per unit time. Then this has to be stored in the interior. Then heat which is generated, so plus dq source. And all of this has to be stored, so this heat fluxes have to be equal to the heat stored in the interior. Now, we have already expressions which describe us these last two terms. We still have to find these. And we say the heat flux is caused by conduction. So obviously we have to use now Fourier equation. But before we do this, we will do a general consideration on this difference between dq and dq dash. And this is something which is continuously done in physics when one has to derive. We want to find the difference between two quantities, two fluxes, which are a very small, an infinitely small distance apart. And since the heat flux can obviously change only in a continuous way, then the change from this quantity to this quantity, because it occurs only on an infinitely small distance, can only be a very small amount. And let's try to write this down. So dq dash, since I want to go now in direction of n, so the difference between the heat leaving at a larger amount of n minus the difference, the heat flux entering. No, excuse me. Let me write it in this way. dq dash is equal to the heat flux leaving here is equal to the heat flux dq plus an infinitely small change of this heat flux plus a differential of this small heat flux. Now, but this is really not clear enough as I have written it, because again I want to indicate that the change in the heat flux occurs as a consequence of the fact that I have have moved along n by the amount of the dn. For instance, not by a change in time. I just moved from, let's say I have in this heat balance to consider the difference between these heat fluxes at a certain moment. So I write this in order that it is clearer, and maybe I make just some brackets around here, because this is only a, let's say, not a very clear writing. dq plus the change, so I write a partial differential sign. And I have to indicate that the change is when I change the n. So I write over n of dq. And then, since this would be obviously something different, I have now divided, this is a change per unit length. I want to have the change on a small distance dn. I multiply this once more with dn. So let's say, as far as the quantities are concerned, the dn would drop out, and the equation is the same as here. But in this way, I know that the change is meant by as a consequence of the change in location. Okay, now for dq itself. Then we use Fourier's equation. Well, first, this is the heat flux per unit area. So in order to get the amount of heat which flows through the area element dA, I have to multiply my specific heat flux with dA. And then I just enter this here, minus k times dt over dn. Okay, now what I need here in my energy balance, and maybe I just underline this because this is really the basic physical consideration which I use for my purpose, I need the dq minus dq dash. Which, from this equation, dq minus dq dash would be minus this quantity, minus d differential, or I can, this is completely equivalent. It's maybe more convenient than to use, I can write it in this way. Which again would be written d of dq over dn times dn. And now I just put this term in here for the dq. Now minus minus cancels out, so I will have a plus sign, and I have d over dn of this term here, k dA times dt over dn. And now I'm essentially through. All I have to do is now to introduce this here and these two terms into my first equation in order to get, let's say, my final result. So let's do this. This is this here, d over dn of k dA times dt over dn plus source term, this here, phi times dA dn is equal to the heat stored, which is this term here. C rho dA dn dt over dn, dt over d tau, excuse me. And I see that I forgot something here, yeah? I forgot the dn. It is here. Now you see the dq I have introduced, but I should have put the dn in. And this then goes in here also. And this means then that I can cancel out the dn. And then usually the equation is presented by solving it for the temperature variation with time. So let's do this here, dt over d tau equal to, and I have now to multiply through by this term here, 1 over c rho dA times d over dn of k dA dt dn plus, here the dA cancels out too, so I have just phi over rho c, 0. What did I write? 0. And this then is an equation which I can use to calculate a temperature field, and we will do this very soon for some specific simple geometries which occur quite often in nature, so that we would like to know the situation explicitly. Maybe I can just point out, of course, in order to make any kind of calculation on the effect of heat conduction, I have to know the heat source. I would have to know what kind of chemical reactions occur and what is the heat generated or absorbed by such. I have to know the material, which means then I can, from reference books, take values for specific heat, for density, for thermal conductivity, which are all properties of the material involved. Now, still, in order for this equation to be useful, I have to know something else, because really, let's say, it tells me, let's say, it contains here as a parameter the directions of the heat flow lines. I have to know the heat flow line, so I have to have an idea of the qualitative idea of the temperature field. I have to know qualitatively the temperature field, but we will see that in a number of important cases we know this. So this would be the general equation, and now, as I say, we want to apply them to some special situations. I would like to make some space for this purpose. First thing, this equation is quite general in that it holds, let's say we have considered that the temperature may change with time as well as locally, but we will at first look at situations which are steady situations. This means no change with time. Well, this obviously means this is, for instance, a change with time would always written as the differential of something in time. So if we say steady, this means differential of anything. Temperature, for instance, with time equals 0. No change in time at a specific location, and this is what this means. And we will also at first, later on, it might be useful to look at some cases with heat sources, but we will at first look at a situation where we have no heat sources, phi equals 0. Now, this obviously simplifies our equation already considerably, because this term is 0, this term is 0, so the middle term has to be 0 also. Now, unless any of these quantities would be infinite, so that then the reciprocal would be 0, which of course they are not. Specific heat densities are all finite quantities, well, and surely we don't want to have an area element which is infinite. This means this term remains finite. If the whole thing has to be 0, this means the second term has to be 0. So this differential which we have here in this expression has to be 0. In addition, we have something else. Here we use the partial differential sign because the temperature, and we are interested in calculating the temperature, depends for a general situation on location as well as on time. If we have a steady situation, then the temperature in a stream tube, along a stream tube, depends on location in the stream tube alone. So this means we can again forget about the partial differential signs. We can write again total differential signs. And we can write d over dn of k dA times dt over dn equals 0. Now, what does this mean? If the change of any property, let's say here, for instance, of this quantity, which is here in the bracket, along the normal to the stream tube along n is 0. Let's see what this must mean. If we would plot our coordinate along the stream tube n here, and we would plot this, let's say we would just call this simply f, capital F. And we would plot this f here. Then what this expression says, there is no change in this quantity along n. Or, with other words, if there is no change, the quantity itself is constant. So we can immediately, instead of writing this, can now write that this quantity itself, k dA times dt over dn, has to be constant. So this holds for all steady situations. Now we will go to some specific geometry. And as a first one, we will look actually to the one which we have considered in our first lecture, that is a plane wall. Now, this would be the two surfaces of the wall. The thickness of the wall would be B. We will prescribe again the two surface temperatures, T, surface of the wall. I think the last time we called this TW2, so let's do the same thing. This we call TW1. We assume that the surface temperature is uniform along the surface. Actually, you see what we do is, and this is generally in conduction, we have to know something what happens on the boundaries, on the surface of our body, in order to be able to calculate what happens in the interior. We can either prescribe various things. Here we prescribe the wall temperature. We could also prescribe, let's say, a fluid moving along here, and we could prescribe the fluid temperature. We did this also in the first lecture. But here, since we are actually in the moment only concerned in calculating the conduction, the temperature field in a solid body, we assume the simpler situation that we know the surface temperatures. Okay, then the next thing is to ask, well, what shape do the isothermal surfaces have? What shape do the heat flow lines have? Obviously here, as we have already discussed before, the isothermal surfaces are just planes parallel to the surfaces of the slab. And the heat flow lines, since they are normal, must be just normal to the surfaces again. And if we draw a stream tube, it would look like this. For instance, a stream tube which at this one surface has a surface area dA. Obviously then for this specific situation, for the plane wall, the dA is constant, doesn't change. So from our concept of the stream tube, we can say in this specific situation the A is constant. So this means if the dA is constant, then this parameter k dTTN has to be a constant too. So we have k dt dN is equal to a constant. Actually, if we compare this with our Fourier's equation, which for steady state would have here total differential signs instead of the partial differential signs, we see already what the meaning of this constant is. The meaning of the constant is just minus q. So really just from our energy equation or from our heat balance equation, we come back by this consideration to the to Fourier's equation. And then of course we can still go on. If we have now, and this shows us really one more restriction which we should have made in the beginning, but I wanted to wait until I can demonstrate this in order to get the equation with which we started out. If we assume now that the k is constant, pardon? Oh, here we have this equation. Now from here we know that the dA is constant, yeah? Okay. So the k is constant. This means this is constant, so the dTTN has to be constant too. A dTTN constant means that the temperature drop or temperature increase, whatever it is, per unit length in the direction normal to the wall is the same at each location, is constant. And this means the temperature has to drop in a linear way in the wall. So we see that actually the statement with which we started out, which we said is, for instance, supported by measurements, that in a plane wall, the temperature just drops in a linear way from one surface value to the other surface value, is in agreement with general Fourier's equation. That's a kind of support of this equation, which of course in this form is not quite easily checkable, because we would have to have measured infinitely small temperature differences on infinitely small distances. Okay, so for the plane ball we don't learn anything new. Well, we have learned one thing, that really we have to ask for a constant. We can consider this, let's say, we have the linear temperature drop only when for a material for which the K is constant. If the K, we have seen in diagrams, the K in general depends on temperature. Now this would mean then if we have large temperature variations, so that this K variation with temperature is large, we would not get a linear decrease. Well, maybe we can just get then to the form of the equation with which we started out to close our circle. Now, obviously, we can then write K. Now, instead, since this depends this for, let's say, the temperature gradient, the temperature variation per unit length is the same, whatever the size of the dn is which we use. The ratio is always the same. We can just as well say this is equal to this temperature difference divided by B. Actually, we have to write T, because we count n normal in this way, we have to take T1, the TW1, the one further away, minus TW2 over B. And this is Q. Now, in this situation also, we know we can, from the physics, of course, say that the heat flux will be uniform, will be the same anywhere, so that we can say, let's say this is the heat flux Q per unit area, so the heat flux over a finite area we obtain by multiplying this heat flux per unit area with the finite area, let's say with the total surface area of the ball. And if I put the K on this side, as a minus sign on this side, then this is equal to lowercase q times A, well, maybe I write it down, or this we call the heat flux in itself through the area. And this is the equation with which we started out. We didn't write the minus sign, but we turned the temperature difference around. So, now, but let's go to some new situation, which surely occurs quite often too. Let's say we would have, oh, no, excuse me. I think I still would like to say something more about the plane ball. One situation which is quite often found is this, that we might have two balls in series of different materials. So we would have one ball with a thermal conductivity K1, another ball with a thermal conductivity K2. Again, we will assume that we know the temperatures of the two external surfaces of this composite wall, so we will call this in the same way as before, TW2, this TW1. We don't know the temperature on the place where the two walls come together in the interior surface. Let's call this TWI. Now again, for instance here, if we, with this equation on the simple ball of uniform material, if we know the temperature difference, we can, with this calculation, calculate with this equation, calculate the heat flux. Now here we would again want to calculate the heat flux, Q. And in a steady state, obviously again, the heat flux has to be the same through any isothermal surface as I move along, because in steady state no heat is stored in the interior. And in addition, of course, we have assumed here heat generation in the interior is zero. So I would like to know, to have an equation which combines the heat flux with the two known surface temperatures. Well, I can immediately write down an equation for the heat flux as a function, for instance, of these two temperatures. It must be exactly the same as before. So I can write Q is equal to, and in order to get rid of the minus sign, again, I turn the temperatures around. K times A times, and now I have, instead of T1 minus T2, I have to write this at first, the temperature which is upstream. T vol 2 minus this one here, T vol I. And again, and I have to write K1 because I'm in the material with the thermal conductivity 1, K1. I can write an equation. Oh, thank you. Yeah, that's right. B1. Let's call this B2. So I have to divide through by B1. Okay, yeah, sure, I have it there too. Let's see, it's a B. Now, for the second wall, I can write the same thing. K2 over B2 times A times T upstream is now TWI minus downstream in heat flow direction is TW1. Now, what I want to do from this equation is to eliminate the TWI, which I don't know. So, in the same way as we did it actually in the first lecture, let's solve both of the equations for the temperature difference, because then if I add the two equations, then I have a minus TW1 plus TWI1 plus TWI, and this will fall out. So I have TW2 minus TWI equal B1 Q over K A, that's it. And TWI minus TW1 equals B2, and this should be K1, yeah? B2 Q over K2A. And now, as I have said, I will add the two equations, then I get TW2 is equal to, let's see, well, I will take the Q over A out, times B1 over K1 plus B2 over K2. And this is really the answer which I want. If I want to calculate the Q, all I have to do is to solve this for Q. So I get Q is equal A divided by B1 over K1 plus B2 over K2 times TW2 minus TW1. And of course I could continue this with any infinite number of volts in series. Maybe just one thing which is quite interesting to look at this in this connection. Let's assume we would have, for instance, this situation. This would be a metal wall. And this would be a wall of a material with low thermal conductivity. Let's say a plastic. Let's assume the B1 and B2 are of the same order of magnitude. Then I know that metal has, if you check into the properties, has a very much larger thermal conductivity than the plastic material. So K1 is very much larger than K2. Now, this means The B, I said, I assume to be of the same order of magnitude. The K1 is very large. This means this term will become very small compared to this term here. So this means really then I can almost, if this is by an order of magnitude difference, the K1 from the K2, I can forget about this term. And the heat flux as a consequence of the temperature difference in this composite wall is just determined by the material with a purer thermal conductivity, whereas the one with a good thermal conductivity just doesn't enter practically into the consideration at all. Another situation, I think, which is of some interest and which we will just discuss now in a qualitative way would be, let's say, again, we have a composite material, but the composite material would be such that it consists of a very large number of very thin layers arranged in this way. Again, it would be layers of alternately different material. Let's say again a metal, a plastic, metal, plastic, metal, plastic, and so on. Or let's go to the characteristic then is that one of the layer has a very large thermal conductivity, the other has a small, large, small, and so on. And let's go in the moment to the extreme. Let's say only one of the material is conducting, the other material wouldn't be conducting at all. And again, we apply to the two surfaces a temperature T wall 1, 2, uniform over the surface, over the other surface, a temperature T wall 1, uniform over the surface. Question, in which direction does the heat now flow? Obviously, there can be no heat conduction crossing the material which has a thermal conductivity 0, which doesn't conduct at all. So this means really the heat flow has to go down in the various metal strips, which is a situation which we have not looked at before. You see, so isothermal surfaces will still be obviously planes parallel to the surfaces, but now the heat flow lines are not normal to the isothermal surfaces, are somewhat inclined. And this is the case in any kind of material where the thermal conductivity is different in different directions. Here, of course, the thermal conductivity in the direction normal to the layers is 0, because there are always layers which have no heat conductivity. So we have here an example of a material which, as we say, is anisotropic, has conductivity in one direction different from the conductivity in the other direction. Whereas before we have always considered isotropic material, where the thermal conductivity is completely independent of direction. Now we have quite some materials which are of this nature. Well, in engineering, for instance, wood would be such a material. One finds that in the direction of the fibers, the conductivity is different. I think maybe in biological systems this could occur too. In a muscle, probably the conductivity in the direction of the fiber might be different from the conductivity normal to the fiber. So one has to keep this in mind, that let's say our calculation here which we have made are for a isotropic uniform material. Of course, if we have gone here to the extreme, if the situation would be metal, plastic, metal, plastic, this means good thermal conductivity, poor thermal conductivity. Still, obviously, the thermal conductivity in this direction would be smaller than in this direction, because the heat can readily flow down the metal strips, whereas here it has always to cross through poorly conducting material. But there is a certain conductivity in this direction too, and we would find that the heat flux doesn't go parallel to the lamination, but in some other direction. But still, it wouldn't be in the direction normal to the wall. Okay, and well, I think we can just start a little bit with a different geometry, which I would like to look at, and I take this out here. This is correct. Yeah, in this case you could calculate. Let's say so. You could calculate if you take, for instance, an individual strip. Then you could say, well, I know the cross-section of this conducting material. I know the length. So I just apply this equation to this situation. But of course, it's only so simple in the extreme case. If I have, let's say, some poor and good conductivity, then it doesn't go quite this way. Oh, the heat flow lines, yeah? No, the heat flow tubes, the flow tubes. Well, if the layers are very thin, so that you can neglect that in reality, let's say you have some stripe where heat conduction occurs, some stripe where no heat conduction occurs, where you average, so to speak, over a larger number of things. Then the heat flow tubes would again just go down somewhere. You could, let's say, select one tube in this direction down. That's correct, yeah. Oh, in the mixed. This is very much more complicated. If you are interested, I have really such an example in the German as well in the English book, which I mentioned. I think it would be too complicated really to go through this situation here. I just wanted to point out that one has to be careful that things like this can occur. Yeah, now, just to start briefly on the next situation which we want to consider is if we have a spherical shell. And let's say we have an inner space and we have and we will assume it a thick spherical shell. And again, there might be some heat generation in here. I don't know, it might be even in what an example in a biological system would be, but let's say some chemical processes going on here, so that the temperature on the inner surface of this shell will be raised to a value, say, TWI. Somehow I cool the outer surface of this shell so that it will be at a lower temperature, TWO. Again, of course, I have to know the thermal conductivity, and I have to know the geometry. This means I have to know the radius here, Ri, and I have to know the radius out here, Ro. The problem is now, if I know these two surface temperatures, what is the heat flux through this shell, which is caused by the conduction process? And again, since the equation up to here is general, we didn't have to restrict in any way the geometry, we can start out with this equation. But again, we have to know how the dA varies with n. Now, again, in this situation, obviously, we can easily determine the shape of our isothermal surfaces. If the temperature is constant along this spherical surface, obviously, then the isothermal surfaces in between will be, again, spherical shells. And the heat flow lines must be normal to those, so will be just radial lines going out in this direction. So this means obviously that my dA, and I said, let's say a stream tube would be, for instance, this here. So I see here the dA is not constant, but increases with radius, and this I have to feed now into the equation. And I can, from the geometry, determine how the cross-sectional area changes with radius. Actually, maybe I show you the next time. I will just write it down here. One finds that if I consider this now, this would be now a situation in space, yeah? A cone which goes out from the center of the sphere towards the outside. And if I prescribe the opening angle of this cone, then one finds that the dA, the cross-sectional area at various radial distances, is proportional to the square of the radius. I think I can show this the next time. So we would have the statement that dA is R square times a constant, let's say C dr squared. And this I have to feed into the equation. Well, maybe we just can't finish up. Then I have to write k times c times r squared times dt. Now, the direction of the heat flow lines is the radial direction, so I write for dn dr is equal to a constant. If I assume again a material with a constant thermal conductivity, we will come back to see how situations change if the thermal conductivity varies. And this is a constant, this is a constant. So the rest, r squared dt dr, has to be a constant too. And this is then the equation with which we will start out the next time. And I have to, again, let's say what mathematicians say, integrate this equation. I think I can demonstrate in a simple way what this means in order to find then how the temperature varies in the spherical shell, and then also get a connection to the heat flux.